We shall let A be the event that the first fuse is defective, and B the event that the second fuse is what? Is defective. Then we interpret A intersection B as the event that A occurs and B occurs after A has what? Has occurred. The probability of us removing a defective fuse is 1 out of what? Of 4. Then the probability of removing a second fuse from the remaining is 4 out of 19. Therefore, the probability of removing the probability of A intersection B is going to be equal to the probability of is equal to a quarter times 4 out of 19, which is equal to what? To 1 over what? Over 19. Two events A and B are independent if and only if probability of A intersection B is equal to the product of probability of A times what? Times probability of B. Therefore, to obtain the probability that two independent events will occur, we simply find the product of their individual what? Probabilities. So if the product of their individual probabilities gives us the probability of A intersection B, then we conclude that they are what? Independent. Else they are not what? Independent. If in an experiment the events A1, A2 up to AK can occur, then probability of A1 intersection A2 intersection AK is equal to probability of A1 times probability of A2 given that A1 has occurred times probability of A3 given that A1 and A2 has occurred up to probability of what? Of AK. Okay? A collection of events A1 up to AN are mutually independent if for any subset of AI1 up to AIK for k less than or equal to n, we have probability of AI1 intersection probability of intersection probability of AIK is equal to the product of their individual what? Probabilities. Remember that this condition is true if they are what? If they are independent, and they are independent, then the intersection of the probabilities is equal to the product of the individual what? Individual probabilities. This is what this rule is saying. One of the most important theory in probability is the Bayes what? Is the Bayes theory. If events B1, B2 up to Bk constitute a partition of the sample space S, if these are partitions of the sample space S, where the probability, each of these probabilities is not equal to 0, then for any event A of S is equal to the sum of the probability of each of these events times the probability that event A has occurred given that each of these events has what? Has occurred. Or probability of A is equal to the sum of k equals to 0 to n probability of Bi times probability of A given that Bi has what? Has occurred. Hence, partitioning of the sample can be shown as what? As below. Here, we see that this is the total sample space. So these are the partitions. The partitions. The partitions. The partitions and the what? And the partitions of the what? Of the sample space. and this is the event A. Is the event what? A, which comprises of part of B3, part of B5, part of B4, and part of B1. Okay? So the Bayes rule says that if the events B1, B2 up to Bk constitute a partition of sample space such that B is not equal to, probability of B is not equal to 0 for I equals to 1, 2, 3 up to K, then for any event A in S such that probability of A is not equal to 0, we know that the probability of B given A is equal to the probability of B R times the probability of A given BR over the sum of the probability of BI times the probability of A given what? Given BI, for R equals to 1, 2, up to what? Up to K. For example, a manufacturing firm employed 3 physical plans for the design and development of a particular product. For cost reasons, all 3 are used at varying times. In fact, plans 1, 2, and 3 are used for 30%, 20%, and 50% of the products respectively. The defect rate is the 3 procedures as follows. Probability of defective given that is product 1 is equal to 0.01. Probability that is defective given that is product 2 is 0.03. And probability that is defective given that is product 3 is 0.02. Where probability of D given Pj is the probability of defective product given plans. If a random product was observed and found to be defective, which plan was most likely used and thus responsible? So let's look at the solution. From the statement of the problem, we know that P1 is equal to 0.3, P2 equals to 0.2, which is here, and P3 equals 0.5. We must find probability of P given D for J equals to 1, 2, and what? And 3. Okay? Remember, P1, P2, and P3 are partitions. Okay? Are partitions. Therefore, using Bayes rule, we know that probability of P1 given D1 is equal to the probability of P1 times probability of defective given the plan. Okay? Remember, you first select the plan and then you what? You determine whether it is defective or not. But the reverse is not true. That's why we need to apply the concept of what? Of Bayes rule. Divide by probability of P1 times probability of defective given that it is plan 1 plus probability of plan 2 times defective given that is plan 2 plus probability of plan 3 times probability that is defective given that it is what? It is plan 3. This is the total probability, okay, of defective. Okay? Hence, probability of P1 given that it is defective is equal to 0.158 when you substitute into this part, you get 0.153. Similarly, applying the same concept, probability of P2 given that is defective is given by 0.316. and probability of P3 given that is defective is equal to 0.526. Now, random variables. What is a random variable? A random variable is a function that associates a real number with each element in the sample space. It associates real numbers, okay, with each element in the what? In the sample space. A random variable for which a 0 and a 1 are chosen to describe the two possible values is called a Bernoulli random variable, okay? If there are two possible choices, it is called a Bernoulli random what? Variable. If the sample space contains a finite number of possibilities or an unending sequence with as many elements as there are whole numbers, is called a discrete sample space. Okay? If there are finite number of possibilities, we call it a what? A discrete sample space. If the sample space contains an infinite number of possibilities equal to the number of points on a line segment, this is called a continuous sample space. Okay? A random variable is called discrete random variable if its sets of possible outcome is countable. When a random variable takes on values on a continuous scale, we call it a continuous what? Random variable. Okay? The set or ordered pairs, say x and the f of x, is a probability function, probability mass function, or probability distribution of the discrete random variable x if for each possible outcome x, f of x is greater than 0, the sum of the f of x is equal to 1 for the discrete, and probability of capital X equals to small x is equal to f of x. For example, a shipment of 20 similar laptop computers to a retail outlet contains 3 that are defective. If a school makes a random purchase of 2 of these computers, find the probability distribution of the number of defectives. Okay, let's look at the solution. So let x be a random variable whose values x are the possible number of what? Defective computers purchased by the what? By the school. Then x can take a number 0, 1, and 2. Okay? Remember, a school makes a random purchase of 2 of these computers. Okay? So it is possible that all the 2 are defective, or it's possible that 1 is defective, or none is what? Is defective. So the probability of 0 is defective, 1 is defective, or 2 is defective is given by this formula. By this formula is equal to 3, 0, 17, 2, and then 22. In other words, this bracket here shows us the different ways of what? Of selecting a 0 and what? Of selecting 0 from 3 and 2 from 17. Okay? And whereas this one shows us the different ways of selecting 2 defective from 20. Okay? Remember, you select 0 defective and 2 which are not defective. So 2 is being selected from the remaining 17. Okay? Remember, 3